All right. Today we will be learning about graphing trigonometric functions. Trigonometric functions. And let's jump right into it. If we start out, our job is going to be to graph each function. Going to identify the domain and range. And we are also going to describe the amplitude and the period. All right, so we got some new vocabulary terms in there, amplitude and period. We're going to find out what those mean in just a second, but let's go ahead and look at an example. Say I gave you y equals the sine of x. All right. In fact, let's make it a little easier. I'm going to actually, you know what? Let's leave it like that for now. Let's leave it like that for now. Here's a little thought bubble. Before we get into y equals the sine of x, think back to what y equals x looks like, right? We all know that that should be a straight line passing through the origin. Y equals x squared. We know that's a parabola. Parent function looks something like that. If I give you y equals the absolute value of x, you know it would be a V shape, right? So we know about these general graphs, but what about if it was y equals the sine of x? All right, what I want you to do, pause the video for just a second, take a guess, make a prediction. What do you think this graph is going to look like when you plot it on an XY coordinate plane? All right, now I'm not sure how good your predictions were, but let me just go ahead and skip to the chase. Here's what the graph of y equals the sine of x looks like. Now I'm just going to put it out there, and I'm going to explain why it looks like the way it does in just a second, all right? I'm going to start by putting on 5 what I call critical points. It's going to go through the point 0, 0. I'm going to be marking off the x values and angles. So I'm actually going to use radians. So 2 pi, 0. That's going to make a little more sense here in a second. Remember with the sine function, you're plugging in angle values, and then you're looking at the y coordinate on the unit circle for sine, right? So here we go. The next one is, let's see here, pi comma 0. Up here, I'm going to have pi over 2 comma 1. And then down here, I got 3 pi over 2 comma negative 1. So if I connect those dots, this is going to be ugly, but I'm going to try. Connect those dots. You end up with a picture that looks something like that. Okay. All right. First off, let's talk about why this graph does what it does. And I got these 5 critical points here. And you have to remember that when you're plotting or when you're graphing a function, really all you're doing is you're plugging in a bunch of x values and you're getting out a bunch of y values. You're plotting them on a graph and you're connecting the dots, right? So here it is. I have x going into the function. Whoops. Let's see here. I have x going into the function, and my y values are coming out, but the y equals a sine of x, right? So think about what this is saying. Over here, I got the point 0, 0. That's saying when I plug in a 0 for the function, the y value that comes out is 0. That's what it means to have the point 0, 0. 0 goes in, 0 comes out. Now, in order to understand why that is, you got to think back to your unit circle. This is saying the sine of the angle. Remember, when you're using sine, these x values are actually angles, right? Let me do it over here. These x values that you're plugging in are angle values. So if I go to the unit circle, I'm looking for an angle of 0 radians. And you guys should know that 0 means, oh, I didn't open up off of the x-axis at all. It's right here. The sine of 0 is asking you for the y value of that coordinate. Whoops, that's the x value. The y value of the coordinate, which is 0. Hence why the sine of 0 is 0. Remember, when you're doing the unit circle, the sine is asking you for the y value of these coordinates. The cosine is asking you for the x value of these coordinates. Not to be confused with when I say over here, I'm talking x is just input, y is output. Input, output, x, y. But when I'm on the unit circle, whoops. When I'm on the unit circle, and I say, oh, sine is the y value, I'm talking about just the coordinates from the unit circle, right? So look, when I plug in an angle of 0 radians or 0 degrees, I get a y value of 0 on the unit circle. So that means the sine of 0 is 0. So 0 goes in, 0 comes out. When I plug in a pi over 2, the sine of pi over 2, all right, go back to your unit circle. Pi over 2, here I am, pi over 2, the y value for sine is 1. So when pi over 2 goes in, 1 comes out. When pi goes in onto your unit circle, here's the angle pi, the y value is 0. That's why I have pi 0 on the graph. If you go to 3 pi over 2, the y value is -1. When you go to 2 pi, the y value is back to 0. So really what I'm doing here is I'm plugging in the angle values for x, or if you want to, you can consider this. A lot of times it might help if you change this x to theta. Maybe that helps you you're less confused. Those are the angle values. So I plug in an angle, and out comes, let me do this. I plug in an angle, and out comes the sine of that angle, which is telling me the y value. So when I plugged in a pi, sine of pi is 0. 3 pi over 2, sine of 3 pi over 2 equals -1. When I get back to 2 pi, I'm back at 0. Now the nice thing about that is these are all easy values on the unit circle. You connect the dots, you get a nice smooth graph. All right, it's not jagged. We're not just drawing, triangles here. So now keep in mind, I can plug in any value of theta that I want, any value, not just limited to 2 pi, because I can keep swinging around this unit circle, right? After 2 pi, I could go to 3 pi and 4 pi and 5 pi, but my y values are just going to keep on repeating as I go around and around and around. So really, this sine function is what we call a periodic function because it repeats itself. Oops, went too high there. It repeats itself. But notice that it's never going to get above 1 because no matter what angle you plug in for the sine, the y value on the unit circle never gets above 1, right? If you look at the unit circle, the biggest y value you see is 1. So that's why it goes, the highest it goes is 1, the lowest it goes is -1, and it keeps on repeating in both directions. If I plugged in a negative angle, like over here, if I plugged in a negative pi over 2, think back to the unit circle, negative pi over 2 would actually land you back down here. And what's the y value? -1. That's why you're going to see the point on the graph, negative pi over 2, -1. So you end up getting this nice, smooth curve, right? Now, before I go any further with that, let's just make sure I'm not feeding you some bull hooey. I'm going to go to the graphing calculator here. And let's see what the graphing calculator says about y equals the sine of x. Okay. I'm just going to restart it here. Second plus 7, 1, 2. Make it large screen here. And I'm going to get rid of that. So we go to y equals. We got the sine of x. If I hit graph right now, you see there's a squiggle. Notice it's not getting above 1. It's not getting below -1. Now, if I want to see a better picture, what you can do is hit zoom, trig, option 7, and that gives you a little better picture, right? Now, notice this is it's a nice smooth graph, and it's going to repeat forever and ever and ever and ever. So, let's answer some of our questions. We were supposed to figure out what the domain and range are. All right, well, domain, that's an easy one. Domain for the function y equals the sine of x or theta, right? You're just plugging in those values. Is, well, domain is left and right. This will go all the way to the left and all the way to the right. So it's all real numbers. Or you could say x is in between -infinity and infinity. All reals. Range. This one doesn't go above y, or doesn't go above 1, doesn't go below -1. So it's everybody in between -1, whoops, everybody in between -1 and +1. All right. Next one on there, we're trying to find the amplitude. All right. And just for the sake of being consistent, what I'm going to do is I try to put, I'll tell you what, let's do it like that. All right. First off, I'm talking about the amplitude. I got to know what the heck amplitude is even saying. So over here, let me put a little vocabulary box. Amplitude basically says amplitude. The technical definition of amplitude is you take the absolute value of the maximum of the highest point minus the lowest point, and you divide by 2. So look, if you look at this one, the highest point it goes to is 1. The lowest it goes is -1. So if you do 1 minus -1, you're actually going to get a value of 2. And then 2 divided by 2 is 1. So this one would actually have an amplitude of 1. Now, here's the shortcut. Basically, it's saying how high off of the midline. So you see how this line, I call it the midline because it splits my graph. It splits my graph in half. It's kind of symmetrical. So how far above the midline did it go? It went up 1, it went down 1. That's why your amplitude is 1. Some graphs are going to go up a little higher. Your amplitude might be 2 if it went all the way up to 2. All right? Some graphs might be up to 3, so on and so forth. So there's your amplitude. Technically, it's the max minus the min over 2 to get the absolute value. Or in other words, in layman's terms, you say how, let's say this. I'm going to say max vertical distance from the midline. All right, amplitude, check, got it. Right now over here, what I'm gonna do is I'm gonna put these are my answers here. I'm gonna put those in red so that everything stays nice and organized. Oops. Missed it. Let's put it in red too. All right, so my amplitude is 1. All right, now the other new vocabulary word was period. So let's define that real quick. Period, which for whatever reason, they usually use a capital T to denote the period. This tells you how often a graph repeats. Or in other words, it's the length of one cycle. So let's talk about what that actually means. If you look at this graph here, you see how it starts at 0, 0, goes up, goes down, comes back to 0 on the x-axis, or sorry, comes back to a y value of 0. And then can you see how this pattern is going to start over again? All right? And what that means is it's really repeating itself every 2 pi units. Now, I didn't necessarily have to start at 0, 0. Even if I started over here at pi over 2, by the time it gets back up to the top, it went a distance of 2 pi units, right? So what we can say here is that the period, or t, is going to be 2 pi. That's how long it took for the graph to repeat itself. So here's a general idea for the y equals the sine of x. Oh, where's my magic box? For y equals the sine of x, if I ask you for the domain, all real numbers, ask you for the range, you know it stretches up to negative, or it stretches up to 1, down to negative 1. Amplitude is how high it stretches off the midline, that's just 1, and it repeats itself every 2 pi. That's what the graph of y equals the sine of x looks like. Okay? It's really not that bad. Now, using the same kind of strategy, and let me go ahead and throw a little box around this too. Oops. Using that same strategy, I want you to pause the video, take a second. Can you figure out what y equals the cosine of x, or theta, is going to look like? And again, I'll give you a hint. It looks a lot like the sine of x. It's a similar idea. So pause the video and hit it. All right. Hopefully you actually pause the video and challenge yourself. But if you didn't, you're a punk. But in any case, y equals the cosine of theta. Same idea. You're plugging in values for angles, and out, whatever comes out is going to tell you where to plot the point. So think about the cosine. If I plug in theta and I'm getting out these values, let's see here. If I plug in a 0, what is the cosine of 0 radians? Let's go to the unit circle. When you plug in 0, so 0 radians is right down here. Cosine is talking about the x value. So that would be 1. When you go plug in a 0, a 1 comes out. When you plug in a pi over 2, now I'm at the top of the unit circle. That x value is 0. If I go to pi, I'm going to be over at negative 1. Cosine of pi, think about pi, is over here. The x value is negative 1. When I plug in 3 pi over 2, I'm going to be back down to 0. And when I get full circle all the way to 2 pi, I'm back at positive 1. So if we plot those points real quick, I got 0, 1. I got pi over 2 comma 0. So I'm going to label that. I got pi negative 1. 3 pi over 2. And then when I get full circle, I'm back to the top at 2 pi 1. All right, so let's take a look at what that would look like. Connect the dots. Squiggle, 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 squiggle. Oh, yeah. Squiggle, 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 squiggle. Oh, yeah. Squiggle, 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 squiggle. Oh, yeah. How did the squiggle dance? How did the squiggle dance? All right, it's a little rough, but you guys get the idea. All right, and it's going to keep repeating just like the sine value did. And if you don't believe me, go to the graphing calculator. Let's try, I'm going to replace that with cosine, and bang. Pretty similar to what we have, right? There's just a little prettier. All right, so there's your cosine graph. Same thing, domain and range. Domain, still all reals. Range, if you can, I'd pause your video and see if you can try to figure this out before you go further. But for now, let's just keep chugging. The range is going to be from -1. The y values go again. I'm going up to 1, down to -1. And then the period still repeats every 2 pi. And the amplitude still stretches up to 1, down to -1, so the amplitude is 1. And there you go. Voila, we did it. Magic box. Really not that bad, right? Not that bad. This is all background information. We got one more to go, and that's our buddy, the tangent. Oops, where's the y equals? That's example 3. Example 3, y equals the tangent of theta. All right, this one's a tricky one. Let's take a look here. All right, now tangent is the funky one, okay? So you gotta, again, I'm just gonna go ahead and break it down for you. It'd be interesting to make a prediction about what this one's gonna look like. So if you want to pause the video and give it a shot, I highly encourage you to do that. I'm gonna go ahead and spoil the surprise here. It's gonna look a little something like this. All right, it's also gonna go through 0, 0. All right. Next point I'm gonna actually put, here, let me make this a little closer. Next point I'm going to put, I'm actually going to go to pi over 4. Pi over 4. I'm just going to draw an arrow. All right. That's pi over 4, comma 1. Then something weird happens here. You end up with this asymptote. And that happens at pi over 2. Okay. Now, if I were to go this way, at negative pi over 4, I'm going to be at -1. And when I get to negative pi over 2, I'm going to get another asymptote. So what ends up happening is I get a graph that's going to look, oh, that's horrible. All right, here we go. Here's my art skills. This is already bad. You're going to get a graph that looks a little something like that. Now, and again, the whole idea behind this graph, it's not just a random drawing, right? It actually makes sense when you plug in certain values for theta. You plug in angle values. Now, let me go ahead and spoil a surprise. It's gonna do that same design, and it's gonna repeat itself. That's it. How fancy can I be? Can I do this? Let's see if I'm really if I really got this down. I'm going to copy this. I'm gonna make it different color. Oh yeah, that is awesome. That's awesome. There we go. So there is your tangent graph, and it's going to repeat itself. So you get something like that, right? Now, again, let's think about why this is happening the way it is, right? When you plug in an angle of 0 for theta, you're now talking about, okay, what is the tangent at 0 radians? On the unit circle, go to 0 degrees, 0 radians. I'm right here. Y over x, 0 over 1, is going to give you 0. That's why when you plug in a 0, you get out a 0. You skip to the next nice, neat value. Notice I'm not doing all the unit circle values for these. I'm just doing the ones that give me nice, neat values. Like pi over 4. When I plug in a pi over 4, the tangent at pi over 4, all right, pi over 4, go to it. There's pi over 4. Y over x, square root of 2 over 2 over the square root of 2 over 2 is going to give me 1. So that's why I see the point pi over 4 comma 1. So now I'm making my y-axis count by ones now. Okay. And look what funky happens when I get to pi over 2. When I plug in pi over 2, I'm supposed to be doing y over x. Well, here's pi over 2. Y over x makes me divide by 0. 1 divided by 0 is undefined, hence why I have this nasty asymptote at pi over 2. When I plugged in negative pi over 4, think about negative angles. Instead of opening counterclockwise, they open clockwise. So negative pi over 4 is really the same thing as 7 pi over 4. So I'm really sitting down here. That y value is negative square root of 2 over 2 over the square root of 2 over 2, which is negative 1. So that's why when I plug in negative pi over 4, I get out a negative 1. And my graph looks something like that. Same thing when I get to negative pi over 2. I get that asymptote because tangent is undefined at negative pi over 2, right? So that's the general idea behind the tangent graph. And again, if you go to the calculator, you're like, hold the phone here. Let's see if that's actually makes some sense. And there it is. All right, there's your tangent graph. Notice this thing is actually going to stretch up and away, right? Because as you get closer and closer to pi over 2, like if I'm plugging in an angle that's almost 90 degrees on the unit circle, if I'm plugging in an angle like right about here, you see how the x value is going to be really short, but the y value is almost going to be 1. So this x value is almost getting to 0. So I'm taking a y value that's about 1 because I'm almost up here at the top. And I'm taking an x value that's almost 0. So I'm really chopping 1 into really, really small pieces. And that's why this graph gets really big, because if I take something and cut it up into small pieces, I'm going to have a lot of small pieces. That's why your y value is shooting up and beyond. So again, domain. Well, this time, I can't say it's all real numbers because I have these breaks in the graph. So you could just say that the fastest way to say it is x does not equal. You see how it happens at like pi over 2, negative pi over 2. The next one would be 3 pi over 2 is where you're going to get your next asymptote. Really what you could say is it's all the x values that don't equal pi over 2 plus pi n. All right. What that's saying is if I go to pi over 2, you know what? Let's leave that for later. Just know that it's not all real numbers. So it's x can't. I'm just going to, for right now, I'm going to say restricted domain because it's going to complicate things a little bit. Really, it's all the multiples of, it's kind of like the multiples of pi over 2, almost, right? So let's just say it's a restricted domain. Your range now, if you're talking about your y values, how far do you go up? Up and up forever. How far do you go down? Down forever. So your range is all real numbers. Let's talk about amplitude. Remember, amplitude was kind of how high your graph stretched. Well, excuse me, this one goes on forever. So amplitude is going to be undefined. It doesn't have a maximum to find it. And the period, aha, this is where it gets a little different. The period is how often it repeats. Well, looky here. Each segment repeats. Well, if I got down over here at negative pi over 2 and I go to pi over 2, this distance, half a pi over there, half a pi over there, together makes a whole pi. This one actually repeats every pi units. So that's fancy. So I'm going to put that answer in red. All right. So there's our tangent graph. Okay. Hip, hip, hooray. We did it. Aren't we awesome? All right. So let's go ahead and throw a little box around that answer so we keep our notes nice and neat. Here's what you need to do. We're going to have a U try here in a second. But first, what I like to do is, let's just kind of summarize. I'm going to make a little chart here. And let's summarize what we just learned about these different graphs, right? So we did sine, cosine, and tangent. So I'm going to say the graph of y equals the sine of x. Let me scoot this over. Y equals the sine of, let's use theta. Y equals the cosine of theta. And y equals the tangent of theta. All right. And if I ask you about, let's see here. If I said the y-intercept, that's usually where you're going to want to start this graph. The y-intercept, and let's go ahead and let's make this whole chart. Y-intercept, let's talk about amplitude. Let's talk about the period. And let's just leave it at that. No, let's go ahead and do more. Let's do the domain and the range. All right. It's a little ugly, but you guys get the idea. You know what? Let me get back to that. You guys deserve the best. There we go. So this is domain. And that's the range. All right. Take a second, pause the video, see if you can fill in this chart, and see if you can notice some similarities. All right. Pause, and let's go. Y-intercept, hopefully you realize that well, let's just see. All right. So if you did it right, you should end up with a chart that looks something like this. All right. And you got the 0. Notice that the sine and the tangent are similar in that they both intersect the y-axis at 0. Right? There it is. There it is. Cosine's different in that it starts at 1. Sine and cosine are really same amplitude, same period, same domain, same range. But when you get over here to tangent, we have a smaller period, so it repeats faster. And we know about the asymptotes for the domain, and then it goes all the way up for the reals, for the range. Okay? So those are certain things you want to keep in mind when you're dealing with these functions. Now let's actually get to what your homework looks like. All right, this is what you're going to have to do on your homework. Here's example 5. Or I'm sorry, example 4. Say I told you to graph y equals 2 times the sine of theta. Okay. Here's what I would do. First thing is you got to think about, what does y equals the sine of theta look like? So I'm going to put this in green. Here's a little thought bubble. Y equals the sine of theta. Well, if you look back at the notes, you know it crosses through 0, 0. What I like to do is go with the 5 critical points. 0, 0 is 1. I know it repeats every 2 pi because that's the period. So I'm going to skip down here to 2 pi and get the ending point. If I think back to the notes, I know halfway through at pi, I'm going to be back here at the center. When I cut that in half, I'm up here at 1. So at pi over 2, I have a value of 1. And when I cut this part in half, 3 pi over 2, I'm down to -1. That's just from the notes. So my sine graph, y equals the sine of theta, would look something like this. But I don't want the sine of theta. I want y equals 2 times the sine of theta. Can you see that all you're doing, you're still plugging in the same x values, but all it's going to do, it's going to take whatever you get for the sine of blah, blah, blah. It's going to multiply that value by 2. So when I plug in a pi over 2 into the sine of theta, I get out of 1. But since I'm doing 2 times the sine of theta, I got to do 2 times 1, which is going to take my actual graph that I want, same x value, it's going to bump it up here to 2. Now, same thing down here. It's going to multiply all my y values by 2. -1 times 2 takes you down to -2. Now, if I multiply 0 by 2, it's still 0. So all of these are still the same. So what I end up with is a graph that looks a lot like the normal sine one. It just stretches a little higher and a little lower. It's still going to keep on repeating though. So you get something like that. All right. And again, just to make sure I'm not feeding you some bull hooey, here's what I'm going to do in the graphing calculator. Y equals the sine of x. Go down, and I'm going to make that one bold. All right, because I got it like that. Let's put in y equals 2 times the sine of x. Here's the first one. And there it is. Same shape. It just stretches a little higher at the top and a little lower at the bottom. So if I look at it, think about domain and range. Well, the domain is the same. That's still all reals. Your range is a little different, though, because now it's not just going up to 1. It's stretching all the way up to 2. So it's going to be everybody from -2 to 2. Amplitude. Here's the big change. That got stretched up to a distance of 2 off the midline. So your amplitude is 2. Your period still repeats every 2 pi. No changes there. So there you go. And we're done. All right. You try can you tell me what y equals the negative? I'm going to do negative 2, no, let's make it 3. Negative 3 times the cosine of theta. What's that going to look like? Try it on your own. All right, just in case you were having trouble here. First off, start by thinking about what the parent function looks like. Y equals the cosine of x, or cosine of theta. We know it starts at 0, 1. It has a period of 2 pi. So I'm going to go over here to 2 pi. And I know I got to get back up to the top. Halfway through, I had to get down to the bottom. So at pi, I'm down here at negative 1. Again, I'm doing the parent function. At pi over 2, that's when I cross the x-axis, so it looks like something like that. You got to be able to graph these parent functions before you can do anything else. So we end up, the parent function looks a little something like this. Notice, guys, I adjusted my y-axis. I know before I was making every 2 lines worth 1. And now I made every 1 line worth 1. And you'll see why here in a second. But so keep in mind, each line on my graph is really worth 1 now. All right, so we end up with a y value of 1 and stretches down to negative 1, and it goes on so forth and so forth. So our job is to graph y equals negative 3 times the cosine of theta. And as you can imagine, just like before, that 3, instead of going up to 1, it's actually going to go up to 3. Now, the only problem is it's negative. So all I'm doing is I'm taking all of my y values and multiplying them by negative 3. Well, 1 times negative 3 is negative 3. That's where my new graph is going to start. Negative 1 times negative 3 is actually positive 3. 1 times the negative 3, negative 3. I'm just taking all my y values and multiplying them by negative 3. The x values haven't changed yet. Y, when at 0, like here at pi over 2 comma 0, multiplying 0 by negative 3 isn't going to change anything. So I'm going to end up with a graph that looks like this. All right, and it would continue in both directions. All right. So now when I look at my new points, it starts down here at 0, negative 3. It passes through pi over 2, comma 0. Up here it gets to pi at positive 3. Down here it's at 3 pi over 2, comma 0. And down here at the bottom it's at 2 pi negative 3. I should have done that for sine too. I have to go back and label my critical points. This one started at 0, 0. It got up to pi over 2, comma 2. Dropped down at pi, comma 0. Then I add 3 pi over 2, comma negative 2. And over here, 2 pi, comma 0, that's unchanged. What would like to label those points? All right, so there's our graph of y equals negative 3 times the cosine of theta. Now we also had to do the domain and range, no problem. Domain, all reals. Range. This time again, it's everybody from negative 3 to 3. Your amplitude. Now it's stretching up to 3, a distance of 3 off the midline. Your period hasn't changed. It's still 2 pi. That's when it repeats. Okay, fácil, ¿no? Okay, we just need to do a couple more things here. So let me throw that box around this answer here. So there's our graph. All right, let's do one more. Let's do the tangent, and then we're going to move on to something different here. So say, here's example 6. Let's say I gave you y equals, let's make it interesting, 1/2 times the tangent of theta. All right. Just like before, I would try it on your own if you can, and I'll meet you at the finish line. All right. But now tangent, again, I got to think about what does the tangent graph look like? Tangent starts at 0, 0. It has the point pi over 4, comma 1. Negative pi over 4, negative 1. Okay, now I'm back to every line being worth 2 here. All right, and then it's got an asymptote over here at negative pi over 2 and positive pi over 2. So here's my parent function. Something like that. Now all this is doing is taking my y values and it's multiplying them by 1/2. So what used to happen over here at negative pi over 4, comma negative 1 is now going to happen at negative pi over 4, comma 1/2. It's taking this graph and it's squishing it in. So the 1 now gets multiplied by 1/2, so he's down over here. So now my new value is pi over 4, comma 1/2. Over here, my new value is negative pi over 4, comma negative 1/2. All right. And the zeros haven't changed. I still have these asymptotes from the parent function. Those haven't changed. So my new graph of y equals 1/2 times the tangent of theta is going to be very similar. It's just squished in just a little bit. So it has the same shape, it just doesn't rise up as fast. So keep that in mind. All right. Now, this is actually kind of interesting because this, your domain, the range, the amplitude, and the period, those are all exactly like you would see on the parent function. So I'm just going to write C y equals a tangent. All right, and just for the sake of consistency, I like to put my values or my answers in red. All right. Okay. Let's keep on checking with this thing. So we're going to do example 7. All right, we're going to do y equals the sine of 2 times theta. All right. Well, it goes a little something like this. I'm going to go ahead and summarize what you need to take away from this lesson. If you learn nothing else from me from this video, you got to know this. When you are given y equals some trigonometric function, let me put it this way. When you have a times some trig function, and then in the parentheses you have b times theta. What this is saying is, say it's y equals 2 times the sine of 3 theta, or y equals, maybe a is 4, and this is cosine, and then this is a 5 or something, right? What a does to the graph is a affects your amplitude. Really, I should say the absolute value of a equals your amplitude. So like if you think back to what we did over here, when I had a 2 in front, my amplitude was 2. When I had a negative 3 in front, my amplitude was positive 3, right? So the number in front affects your amplitude. The number in there with the angle is going to affect the period. But it's not to say that putting a 2 in there is going to change my graph by making it repeat twice as long. Instead, what it actually does is, to get the period, and which, remember, we signify with a capital T, you're going to take the original period for the parent function, and you're going to divide it by b. All right, so let's see what that actually means here. What is the original period for, if I'm thinking of y equals the sine of theta? So here we go again. I'm going to graph the parent function. If I say y equals the sine of theta, you should be getting good at this. Starts at 0, 0, ends at 2 pi. So you got 0, 2 pi, crosses here at pi, gets to its peak at pi over 2, and gets to its minimum value at 3 pi over 2. So here's your parent function. Something like that, right? So my original period is 2 pi. Now this rule is saying my new period is going to be 2 pi divided by whatever angle is in there with the theta, or whatever number is in there with theta. In this case, it's 2. So my new period is pi. So what it's doing is it's taking pi, and I know now I'm still going to start at 0, 0. That hasn't changed. But all it does is it shortens it. So now I'm going to get my whole cycle in by pi. So I'm going to start at 0, 0, and I'm going to end at pi 0, which means halfway through, I'm supposed to cross back through the x-axis. So that means at pi over 2, I'm going to be back at the x-axis. And that means halfway through that, I'm going to be at the peak, and halfway through this half, I'm going to be at the bottom. So I end up with a graph that does the same thing that sine normally does. Oh man, I blew that one. Hold on. Goes up, goes down, except it just happens twice as fast. And so you can keep the pattern going. And it would end up looking like that. So here, when the period is pi, a new period is pi, my amplitude didn't change. My domain and range are still the same, right? But now it's the same graph, it just got squeezed in. So now it's repeating itself twice as fast. And just in case you don't believe me, real good way to verify. Let's go to the graphing calculator. Here's y equals the sine of x. And now I'm going to change it so that over here, I'm going to put in a 2. Graph that. There's the original, and bang. You see how it's getting up and down in the time that this one got through half its rotation. Okay? So that's what a number inside the angle will do for you. Okay? So really what happens is A controls the amplitude, or in other words, it controls how it stretches vertically. And B controls the period, and in other words, it kind of compresses the graph, right? Squeezes it in horizontally. And there you go. All right, so there's your little rule of thumb. All right. Just one last thing, guys. When you're making these graphs, what I'm going to be looking for, I don't need perfect graphs, but what I need is you to label the 5 critical points. Like here, 0, 0, that's where it starts. Pi, 0 is where it ended. Pi over 2, negative 1 was then here at the bottom. I'm sorry, pi over 2, 0 is here. Then here at the bottom, I had halfway between pi over 2 and pi is actually 3 pi over 4. Think about it, this is like half a dollar, and that's a whole dollar. This is 3/4. Over here, this peak point is actually going to become pi over 4. That's halfway in between 0 and pi over 2. So what I need you to do is make sure you label these 5 points. 1, 2, 3, 4, 5. Now, just to verify kind of why that's happening, this is going to be the last thing, I promise, is that if you made a little table here, and now I'm plugging in a 0, right? 0 goes in for theta. 2 times 0 is 0, and the sign of 0, if you look back at your unit circle, is still 0. That's why I have the point 0, 0 here. When I plug in a pi over 4, that's going to make me do the sine of 2 times pi over 4. Well, 2 times pi over 4 is the same as pi over 2, right? 2 over 4 reduces down to just 1 over 2. Well, the sine of pi over 2 is 1. That's why when I plug in a pi over 4, I get out a 1. There it is. And you can continue for the rest of the points. So that's why the graph compresses itself. All right, you should have enough to get going on your homework. So good luck.